Welcome back to the lab. Welcome back to Eve for everyone. Today we're going to pick up our ESD Monitor series by diving into a very important part of the design, and that is component selection. I'm going to walk you through some of the compromises that we made and ultimately explain how we made a couple of these design decisions. This is like one of the most critical steps of designing anything, and basically just want to walk through some of what we did to make sure that we're going to be a effective and safe ESD monitor. I'm always keeping something in mind, and that is, how long is this really going to take to build? How long is it going to take to go from nothing to something? And a big part of that for me and for this channel has been minimizing the amount of time it takes to physically build the device so we can focus on designing, testing, and repeat. And when we're doing a project like this, that means that if I can, I'd really like to limit the components that I pick to components that are cheap, accessible, and cheap to assemble. Now that's a crazy triad of constraints, and basically it's, can we get it freely and availably, but can also a PCB assembler get it freely and availably? And we've been using JLC PCB for a while, and unfortunately, they only have one precision op amp and one comparator in stock, and the comparator is the LM393, and the op amp is the OP07. So unless we have a really good reason not to, we should stick with these components. Now, if we think back to our simulation, we've got a few microamps of current flowing through this monitor, and that means that input bias current is going to be pretty important. If we're stealing 10, 20, 50 microamps of that 100 or 200 microamps, that's going to be a problem. So let's take a look at what we have here. We're looking at something between 20 and 250 nanoamps at room temperature. And once we get that up to maximum temperature, 400 microamps. And this is, of course, considering whether or not we need a buffer before this component. Now, that'll be times 2, and actually it could be per input. So we could be looking at 250 times 4, so about 4 terminals. No, but only 2 of them are connected. So up to maybe 800 nanoamps, up to maybe a microamp. If we look at the OP07, that's a lot better. And we've got the OP07C. They've got the better one. So if we look at the same thing, whole range, 2.2 nanoamps. So we're looking at, what is that, an order of magnitude? Yeah. Wait a minute, 2 orders of magnitude. That's a lot better. The OP07 is cheap, and that seems like pretty cheap insurance. So I think we're going to move forward with the OP07 in mind. So we're going to have a voltage buffer. Maybe we'll do some amplification so we can limit the output voltage actually present to the user. Obviously, this is going to be safe. We're going to use a UL listed power brick, and you have plenty of isolation to make sure that we're not going to hurt anybody. But that's not really handled in this design. That's handled outside of this design. So we can rely on that as we're moving forward. So I guess that makes this pretty straightforward. What we're using here is an open collector output, and that'll let us put a bunch of these in parallel, which is pretty useful. And that means we're going to be asserting a low state, so we'll have like inverted logic. The reason why we're going to use the OP07 is because we don't have a really good reason not to. And they do have these compensation pins here. And I just want to talk about that for a moment, because this has come up before in some of the YouTube comments. So when you're truly using this as a precision op amps, you'll probably need this offset, as that's an offset voltage adjustment. And it allows you to tweak the bias point. They give you an opportunity here to add a potentiometer to like tweak the offset and null it out. They specifically that you can leave it as an open pin if it's not needed. I'm not finding that in the datasheet right now. Give me a moment. Yeah, I couldn't find it, but when you look at the design here, the internal architecture, it becomes obvious why that's the case. What you see is, there's this, you're basically compensating a mismatch between 2 different current sources, and that's what they're saying in here, mismatch transistor pairs, collector currents, current gain betas. So basically imperfections in the die is what you're compensating for. And so what you can do is you can give it a little bit of extra current, and that's pretty awesome. But obviously this is still a fully functional design without that extra current, so you don't need to apply it. Moving on, there's a couple different things that we need to do. We need to indicate that there's an error, and we're going to do that in two ways: audibly with a beeper and visually with an indicator LED. And both of those things get kind of tricky when you want to put this thing in an enclosure. So we're going to have this buzzer that just oscillates on its own. You just apply voltage, in this case 12 volts, and that will turn it on. If we wanted to, we could add a switch that would let you turn it down by adding in a series resistor. To get the light out of the system, we're going to use some of these light pipes. And if you've never used a light pipe before, man, you're in for a treat, because light pipes are amazing. So we're going to have some LEDs on the board, line up some light pipes, got an audio jack. We've got a mono plug that we're going to use as the output for the human monitor, not for the desk monitor. We're just going to use a terminal block for the desk monitor. And the reason why is because there's a ton of these wrist straps. This is one that looks particularly nice. It's got the metal band with two conductors, the mono plug on one end, and then a little like nubbin that plugs into the wrist strap for dual conductor monitoring. There's a bunch of cheaper ones too. I just really like the look of this one. So those are the critical components we need to select, and I hope that you enjoyed walking through some of our rationale for why we picked these. You know, I'd love to tell you that every time I've selected a component, I've done it for a technical reason. I'd love to tell you that every time we've made a design decision, it was because technically that was the right way to go. But there's so much more to it than that. There's availability, there's total cost of ownership for a design. It's how long is it going to take to build the new schematic symbols and capture the thing? And, well, how much do we need to dive into the datasheet because it's a new part? There's engineering time or design time, then there's the assembly cost and the part cost, and all of that factors together into a really complex total cost of ownership. And in the case of an example like this, where we're walking through designs and designs and designs and designs, well, there's not really like an ROI on engineering time, so we need to be mindful of that. But hopefully walking through some of the steps of this was helpful for you. Yeah, now that I think about it, we did kind of gloss through some of the characteristics of the op amp. So if you'd like to see more about that in a future video, let us know if you'd like us to do a deep dive into the OP07 and or the LM393. We got some other projects coming up, and I'm sure they'll need a comparator or an op amp, so we'll probably be talking about these components again. So let me know if you'd like to see more of a deep dive in a future video. That's all I have for today, but if you like this video, let me know by hitting the like button, getting subscribed, or leaving a comment down below. A special thanks to our Patreon and channel members. I really appreciate the extra step of supporting E for Everyone directly. Thank you. Coming up soon, we'll be continuing this project by talking about the schematic capture and the layout of the circuit board. I'm really excited to walk through that with you. But most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching E for Everyone, and thank you for staying till the end. Bye!